All right, in this video, we're going to run a one sample t-test, and we're going to do that starting with Excel and then moving into JASP. Okay, so the data are actually going to be entered into Excel. I'm going to show you that in just a moment. And then we're going to give the data a variable name. Typically, we use the first row of the data file to do that, and we'll do that in Excel. And the convention really is lowercase. So we're going to be going through an example where we're doing a one sample t-test looking at temperatures in Florida in September. We probably will want to give that just a simple name that will then turn up in JASP as, say, TEMP, temp. Okay, and then we're going to save the data to a CSV file. You can do that in Excel. And then we upload that CSV file to JASP. And then we run the analysis in JASP. So the data actually start in Excel and then migrate to JASP for the analysis. Okay, so let's run through how a one sample t-test would work in Excel, and then we're going to do it in JASP. Let's imagine that we have data from temperatures in Florida in the month of, say, September, okay? And we have 5 days sampled. So under the X column are the temperatures in Florida. The mean then is calculated from those 5 observations, and it's 85.80. And then, as you'd imagine, we simply calculate the deviation score, right, which is X minus X bar. And then we do the square deviation score, and when we sum those up, that's going to give us the sum of squares. Right? So we sum up all those square deviation scores, we get 194.80. That is not particularly interpretable. Okay, so, but from there, we want to estimate, because we don't have the population variance, we need to estimate what the population variance is. And so that's why we look right here and you see S hat squared. That tells us it's an estimation of the population variance. And in this case, it turns out to be 48.70. Now, how do we get that? Well, we take the sums of squares, which is 194.8, and then we divide by degrees of freedom, which equals 4. Okay? So 194.8 divided by 4 gives us 48.70. We take the square root of that, and we get the estimated population standard deviation, which is 6.98. Now, in order for us to figure out whether or not this sample mean falls a good distance away from, say, the population mean, we need to know what the population mean is, obviously. Okay, so we know because we're running t-tests we don't have the population variance. But let's just say we're given that the average temperature in September in Florida is 84.15 degrees. Okay? In order to look at where this sample that we have right here of 5 temperatures falls in the null distribution, or the distribution for the population, okay, what we're going to do is we're going to start by calculating the standard error of the mean, estimated standard error of the mean, I should say. And we get that by taking the estimated population standard deviation and dividing by the square root of n. Okay, so when we calculate that, that's going to be 6.98 divided by the square root of 5, and that equals 3.12. So that's our estimated standard error of the mean. Now, where does that go? Well, when we calculate the t ratio, okay, the estimated standard error of the mean goes in the denominator. Okay, so that first step leads to the completion of the overall calculation by giving us the denominator of the t ratio. Now, I use the term t-OBT for t obtained. That just means the obtained t ratio result. Other textbooks may not use t obtained, but this helps identify it as the test statistic. Okay, so then all we got to do is fill out the numerator, right? And we just need the sample mean. We'll go back up to our table. Our sample mean is 85.80. And we're going to subtract out our population mean, which is 84.15. And then we're going to divide by the estimated standard error of the mean, which is 3.12. When we do that, we get 0.53. Now, I have below that Cohen's d as well, but I'm not going to go into how that's calculated right now. Okay, so 0.53, what that means is that This sample that we collected, the mean falls 0.53 standard errors from the population mean. So it's not a very big difference. In fact, we would never reject the null hypothesis over a t-obtained score of 0.53. Now, let's do a couple of things with the numbers here to make it a little bit more interesting. And what I'm going to do is I'm just going to change the value of the population mean. And let's say that the value of the population mean is 81 degrees, let's go 81.75, okay? Now what that's going to do is it's going to increase the size of this discrepancy right here in the numerator. And you can see by increasing the size of that difference, we correspondingly increase the size of the t-ratio. Right now the sample mean is falling farther from the population mean as it is measured in standard error units. Now watch what happens if I decrease the population mean again. Let's say the average temperature in Florida in September is 75.68 degrees. Okay, now watch down here on t obtained. What effect does that have on the t-ratio? Well, as you increase the size of that numerator, the t-ratio gets a whole lot bigger. Okay, now we're getting into territory where we might reject the null hypothesis because the t-ratio or the t-obtained that we've calculated is going to exceed the critical value for t necessary to reject the null. I'm not going to go into whether it does or not, but the point is I'm trying to show that as you increase the value of the numerator, you're correspondingly going to increase the t-ratio, the obtained t-value. Okay. Now the other way we can affect this is by changing the size of the standard error of the mean, right? Or the estimated standard error of the mean. So if I came back up here and said, okay, you'll notice that these raw scores are spread out quite a bit. What if we left the population mean at 75.68 and then I made all of these scores a little bit more consistent? And you'll notice that it's updating as I do this, but I'm going to really restrict the variability, right? See how I'm like putting them all really close to one another? So now the sample mean is 75.40 and our population mean is 75.68. So there's hardly any difference between the sample mean and the population mean. That of course affects all these discrepancy scores, the sums of squares. And as we get down here now to the estimated standard deviation, it's shrunk all the way to 1.14. Okay, so now when we calculate the estimated standard error of the mean, look how small it got, right? It's down to 0.51, and our t-ratio is now negative 0.55, almost close to 0. So the other way that we can affect the size of the t-ratio is when we have less and less variability actually within our sample. Okay, so I'll spread the variability out again. I'll try to keep the mean at around 75 or so. So let's say I go 80, 70, 90, 60. So it's now at 75, and here it's 75.68. Now look what happens. So I've got a lot more variability in my sample, right? That's going to increase the size of the estimated standard deviation for the population, right? So what effect does that have? Well, now we're increasing the numerator in our calculation of the estimated standard error of the mean. That gets really big, right? So now we've made the denominator of the t-ratio that we're calculating large without really changing a whole lot, the numerator. That is going to actually make for a smaller t-ratio, right? So because when you have larger denominators, you're going to get smaller results. Okay, so we can play with this a lot. Now we're going to go in just a second, and we're going to take this data and we're going to put it in JASP and see if we get the same results. So give me just 1 second to do that, and I will be back. Okay, so what we're going to do now is take the data from Excel, save it as a CSV file, and then put it into JASP. So I did all of that already, and I'm going to pull JASP over now. Okay, so you can see the data right there are exactly the same. Okay, and just as a refresher, if we go down here, the population mu we had set at 75.68. So let's hold on to that for right now in our short-term memory. But right now we have all of our data in JASP, and we're going to run a one sample t-test. Okay, so we can do that by going under t-tests and then clicking on one sample t-test. Sounds pretty intuitive, right? Okay, so here's our one sample t-test. First thing we do in JASP is we're going to pass over the variable that we want, right? So we pass temp over, and you'll notice right away it's sort of updated in the panel to the right, which is our output. But it's not giving us the correct result yet because we haven't told it what the value of the population mean should be. So when we come down to these selections, we're running a student t-test, that's fine. And then it says test value right here, okay? So if you see test value, it's set to 0. We don't want it set to 0. In fact, we're going to go back, and again, let's take a look. What does our population mean? 75.68. That's what's meant by the test statistic. It's just the population mean. So I'm going to enter that in right here, okay? And you'll notice now that it has updated, and it gives us the t-test result, right? There's no calculation of the estimated standard error, the mean, or anything like that. It just does it all automatically, which is very cool. And the result it gave us was negative 0.136 with 4 degrees of freedom. Now, just to recall, if we go back to our Excel sheet, right, what did we get? Negative 0.14 with 4 degrees of freedom, right? So we got exactly the same result as what JASP got, which is comforting. We should get the same result, okay? So that provides the primary output for the t-test. Now, there are a couple of other things that you can do that I'll show you just really quickly. Okay, one is you can check the assumptions for the t-test, and one of the assumptions is that the underlying distribution is normal. And this test you will like to see to not reach significance, okay? Because if the test is not significance, it tells you that there's no reason to think that the underlying distribution is not normal to begin with. So you're looking actually for big p-values here, okay? So, and that'll show up as test of normality, Shapiro-Wilk, and you can see here that the p-value is actually very large, close to 1.0. So that means that you can feel comfortable feeling that the sample conforms to a normal distribution. Okay. The other one that I'll show you is you can also plot out your descriptives just by clicking on descriptives. Okay, and then up comes the n, the mean, the standard deviation, and the standard error. So that's kind of cool. You can do descriptive plots along with it. Right? So that gives you your error bars, and it also shows the mean in your sample. Okay, and you can also calculate the effect size to go with the t-test. So click on that. Okay, and we'll go back, should show up there as Cohen's d, negative 0.06. Okay, so there's a lot you can do, but you can see how easy it is to actually compute the t-test within JASP. And so basically you just save it within Excel into a CSV file, upload it into JASP, and then just click on what you need. And in real time, it's going to run those statistics, produce the output. And then if you want, you can always copy or screenshot the output and send it elsewhere. For example, if you're doing a homework assignment or something like that.